All right, so first of all, thanks for the invitation to speak here, and also feel free to interrupt me with questions at any time. Okay, so I'm going to talk about exponential concentration of cover times and their relation to Gaussian free fields. Okay, so the talk is going to be in 3 parts. So in the first part, I'm actually going to need to spend some time defining a bunch of stuff, so a bunch of preliminaries. And basically, the goal of this first part is to state the generalized second Ray-Knight theorem, which is a certain theorem that relates random walks with Gaussian free fields. And then in the second part, I'm going to basically be following the work of Jian Ding, James Lee, and Yuval Perez, who were basically the first to figure out how to use these Ray-Knight theorems to relate cover times to Gaussian free fields. But then in that part, we're going to sort of encounter a certain obstacle. And in the third part, I'm going to basically describe a way to overcome that obstacle, and by basically some kind of more detailed understanding of the Ray-Knight theorem. And that's going to allow us to basically give, to sharpen the original bounds given by Ding, Lee, and Perez. Now, okay, so I should mention that after I worked on sort of the stuff in this third part, I found out that actually this idea had already appeared a few months earlier in a preprint of Titus Lupu. And, but that work didn't exactly connect it to cover times. So what I want to do here is basically try to describe the whole story about cover times and Gaussian free fields and their relationship. Let me also mention that, so unfortunately, I'm not really going to be using any chaining in this talk, but hopefully you'll still find it interesting to learn about Gaussian free fields, which are a type of Gaussian process, and in particular, we're going to be really looking at the expected maximum of this process, which is basically the Gaussian width that has appeared in a bunch of other talks and is the sort of quantity that you can estimate using chaining. Okay, so all right, so I guess we can get started now. All right, so our setting is we have a simple graph, vertex set V, edge set E, and fix a starting vertex V naught. And we're going to consider a continuous time random walk on this graph. You'll see in a minute why we do this, but continuous time random walk is just the same as a simple random walk, except that at each step, there's like a variable amount of delay you wait, which is an exponential random variable of mean 1. And so this notation is just x sub t is the vertex you're on at time t. This is basically, you'll see in a minute why we do continuous time, but it's not very different from the usual discrete time random walk. And then let's define the cover time to be the first time that all the vertices in the graph are visited at least once. Oh, by the way, so the walk starts at V naught. And the hitting time between 2 vertices x and y is just the first time a walk started at x visits y. Okay, so then I'm going to need to define this notion of effective resistance, which is just that if you imagine the edges of the graph are all unit resistors, then we just define the effective resistance between 2 vertices to be what the physical resistance would be between them. And okay, so this is not you can sort of think of this almost as a black box, I guess, but let me just describe quickly, I guess, for some high school physics review, how you would calculate such a thing. Well, basically, you can solve for the voltages at each vertex, and then, yeah, so you have to kind of make sure the currents balance out, but then if you kind of solve this equation, here, this delta is the graph Laplacian. So F would be, if F denotes the values of the voltages, and then you can look at the voltage difference to get the effective resistance. Okay, so this is not super important, but this thing here is going to be more important. Let me write it down for future reference. Okay, so we're going to use this commute time identity, which basically says that the effective resistance is more or less equal to the hitting time. Well, it's a symmetrized thing here, but this is one of the ways in which effective resistance is going to come into the picture. Now, okay, so I'm not going to prove this, but I hope this sort of at least seems plausible, because the way you can compute hitting times is also by kind of solving an equation like this with a graph Laplacian and just in figuring out the hitting time. So hopefully this kind of thing is at least plausible, and it's not so hard to show if you just kind of work out the calculations. Okay. So let me just write this down for future reference. All right. Okay, so now I can define the Gaussian free field for a graph. The Gaussian free field is basically a multivariate Gaussian with a value associated with each vertex of the graph. So I'm going to denote those values by eta sub v for each v, and we force eta sub v naught to be equal to 0. And yeah, I guess so. More generally, you can define a Gaussian free field with for any subset. You can take any subset of vertices and enforce that they're 0. For our purposes, our set is just going to be v naught. Okay, so it takes a value at each vertex, and let me describe it further by saying that for a given assignment of values, that's this f here, the probability density of that assignment of values is proportional to basically, well, we look at the sum of the squared differences between adjacent values at adjacent vertices. And we sum that, and then e to the minus 1/2 times that sum. And okay, so this is maybe it's not so clear what this quantity means, but one thing to note is that this is basically saying it's sort of it's encouraging the values to be close to each other for adjacent vertices. And the form that we're going to use more, the form that's going to be more useful to us is a different form here, in which we just describe the covariances of these values. So I'm going to copy this down as well, because it'll be useful later. Okay, so let me explain what this is. So basically, it turns out that the expectation of eta for any two vertices x and y, the expectation of eta x minus eta y squared is just equal to the effective resistance. And this works even when one of these vertices is v naught. So in particular, let's say I take y to be v naught, then eta sub y is just 0, and then I get this thing here. So I can compute the variance of each vertex, basically, the value at each vertex, and then plugging back into this formula, I can get all the covariances. So this is another way of determining this multivariate Gaussian. Okay, so yeah. Oh yes, so these are equivalent ways of specifying what this Gaussian is. Yeah, so maybe let me say a quick word about. Okay, so I guess I'm not going to prove that they're equivalent, but it's not so bad to prove. And maybe like as a sort of vague explanation of why these are equivalent, it kind of has to do with the fact that this thing here is like an energy, and so one way to calculate the effective resistance is actually an energy minimization thing. So yeah, so the relationship is some kind of energy minimization here. Yeah, but I'm not gonna go into more detail about this. Okay, so let me give you an example of a Gaussian free field. This is a graph of a realization of the Gaussian free field for the 2D lattice. Okay, so this is just to give you some idea of what it might look like. Something that's going to be more important for our purposes is actually the Gaussian free field for a path specifically. And so let's say we have a path v0, v1 up through vn. Then, okay, so one way of getting the Gaussian free field for this path, well, if you just plug in these formulas, you'll see that the variance of eta sub vk should be k. So yeah, so it's an easy calculation. One way of getting the Gaussian free field is just to make a Brownian motion starting from v0 here, and then so I mean I'm imagining these v0, v1 up to vn being spaced one apart on the x-axis. Then I can just make a Brownian motion like this, and then the values of my Gaussian free field at vk will just be the value of the Brownian motion at time k. Okay, so this is also a good example to keep in mind. Oops, there I go. All right, so all right. So next, I need to define something called a local time. This is actually a very simple concept. So yeah, so we have our graph in random walk. The local time is defined. So at a time s and a vertex x, I'm going to define the local time L sub s of x to be equal to 1 over degree of x times the time spent at x by the random walk up until time s. Okay, so it's just the time spent at x. It's normalized, so for convenience, it's normalized. It has this normalization factor of the degree of x. But otherwise, it's just how much time we spent at x. Okay, so that's pretty straightforward, I think. All right, and then finally, I have this other quantity that's a little bit stranger, which is tau plus of, so for any time t, I'm going to define tau plus of t to be basically the first time that v naught accumulates local time equal to t. So I'm going to keep running my random walk until I notice that I've spent at least time t at v naught. Okay, so let me write that down as well. So tau plus of t is equal to first time v naught accumulates local time t. And this is, so again, the reason I need to do this is because of some formulas later. But really, you should think of this as kind of analogous to, well, like for a discrete random walk, how long will it take for me, if I start at v naught, how long will it take for me to get back to v naught for the first time, right? Yeah, so we're always starting from v naught, basically. And yeah, so well, that would be, I guess, sort of like for t equals 1, and for t equals 2, it would be like, how long does it take for me to get back to v naught twice, and so forth. I guess what I said is not exactly accurate, so I should have also accounted for that normalization factor. But basically, so really it's 1 over degree of v naught that corresponds to a single return to v naught. And okay, so what is, so for a discrete time random walk, what is the expectation of how long it takes for you starting at v naught to return to v naught? Well, that's actually something you can calculate, because if you run the random walk for a long time, basically in the long run, the amount of time you spent at v naught is going to be proportional to the degree of v naught. And so the amount of time spent in between visits will be proportional to like the inverse of that. So the upshot is basically the expectation. So for continuous time, it's kind of similar. And the upshot is that the expectation we can actually compute explicitly. And so I won't go through all the computations, but basically analogous to the discrete time setting, we have some computation like this, where the expectation of tau plus of t is simply 2 times e times t. Okay, and so as I said before, we only wanted to consider this because it'll show up in some formulas later. So I think for the most part, you should just think of these like tau plus of t as just being equal to 2et deterministically. So what's actually going to happen for the relevant cases that we're interested in, this tau plus of t is going to be sort of concentrated around its expectation, which makes sense because it's kind of like the sum of IID return times. So yeah, so basically you can probably just think of these things as being equal without the expectations, at least kind of on an informal level. Okay, so now finally I'm ready to state the generalized second Ray-Knight theorem. Okay, so it's this thing here, and let me just take a few minutes to explain what this actually says. So what it says is, so there's this parameter t. It can be any positive number. And what it says is, well, let's run our random walk and just keep running it until we notice that at v naught we've spent time t at v naught. I guess there's a normalization there, which I'm gonna gloss over that. And then as soon as that time happens, right? We're going to take a look at how much time we've spent at each vertex. These are the local times. And so I'm looking at this simultaneously for all vertices in V. And yeah, so for example, if x is v naught, then this local time is necessarily equal to t by definition, but the other local times will be something random depending on how the walk went. And then I'm going to take a copy of the Gaussian free field independent of my random walk, and then I'm going to square it and then times 1/2 and then add it to the local time. And now, so at this point, I now have like a bunch of numbers for each vertex that are seemingly distributed in some complicated way. But the miracle here is that it's actually the distribution of this complicated looking thing here is actually exactly the same as something fairly simple, which is just a copy of the Gaussian free field, and then you shift it by root 2t, and then you square it. And it has the exact same distribution as this other weird thing here. So let me say a few words about this theorem now in terms of its history. So Ray and Knight independently proved a version of this theorem basically for paths in the 1960s. And it's called the second Ray-Knight theorem because I guess there's another theorem that looks kind of similar to, takes a similar form, but isn't quite the same, that Ray and Knight also proved. And it's generalized, of course, because they only proved it for the paths at first. And there's actually sort of a long history of basically a lot of people kept further and further generalizing the original theorems of Ray and Knight. And so this particular one is due to Eisenbaum, Caspi, Marcus, Rosen, and Xi. But I guess I should just mention that there are many similar and related theorems by other people. So there's kind of a, yeah, so I guess it's kind of hard to say, like, you know, exactly when, what was the first version of which theorem. But yeah, so basically, there are theorems along these lines by Ray, Knight, Dinkin, Lejeune, Snitman, and others that didn't have room for here. Yeah. What are we assuming about it? So so maybe I wasn't clear about this. It's a simple random walk, so it takes each edge with equal probability. Yeah, sorry. So okay, so this is kind of a miraculous theorem, actually, and maybe at the end I'll say a little bit more about this, but for now we're going to take it as a black box, and actually it's still kind of mysterious. So the only way that people know how to prove this still is by essentially doing, like, calculating moment generating functions or something like that. Well, I mean, there is some other stuff, but I would say overall it's still a bit mysterious, like why this is true. Okay. Okay, so yeah. Yeah, so basically for each step, I'm going to wait an amount of time that's an exponential random variable, and then I'm going to take a step. Then I'm going to wait again, take another step.
So this theorem is sensitive to waiting time being exponential?
Yeah, because otherwise you get, like, sort of non-continuous. Yeah, so the waiting time should be exponential as opposed to something else. Any simple graph is fine, yeah. And I guess you can generalize these to weighted graphs as well, but it's pretty much the same as for a simple graph. Okay, so now we've gotten to part 2, which is how do we get anything about cover times here. Okay, so this is, again, following the work of Ding, Li, and Perez. Okay, so the first thing here, I guess, is just the Gaussian concentration inequality. I guess we've sort of seen this in previous talks. I'm going to gloss over it a bit and just kind of talk about how we can apply it. I'll just directly talk about how we can apply it to the Gaussian free field. Okay, so let's define R to be the maximum of the effective resistances, and by this commute time identity here, that is, or rather, not this identity, by this characterization of the Gaussian free field, that is an upper bound on the variance of each individual coordinate of the Gaussian free field. And then let's define M just to be this expected maximum. That's basically the Gaussian width that we've looked at. Maybe I should mention here briefly that so this Gaussian free field is a Gaussian process. In previous talks, we've mostly looked at Gaussian processes in terms of we have a sort of Gaussian vector with independent entries, and then we take the inner product of that against some set of vectors. Whereas the way I've described it as like I have some Gaussian random variables, but they're correlated, but these two formulations are basically equivalent. You can translate from one to the other. So it's the same thing. Okay, so we have this R and this M, and basically, Gaussian concentration tells us that the maximum of this Gaussian process is concentrated, so it has mean M, and its fluctuations about its mean are of order at most, I guess here I should say at most root R. So that's exactly what the Gaussian concentration inequality says. And I guess I should maybe mention that also the tails are kind of like, it has sub-Gaussian tails, but it's not super important for us at the moment. Okay, so it turns out that in many cases, so what we're going to look at is, well, it's going to be sort of the case of interest for us is when this maximum is actually concentrated around its mean, which would correspond to the case where root R is much less than M. And this is true for many examples, like the complete graph, the discrete torus, regular trees. I note here that it does not hold for a path, so not all natural graphs will have it, but a good number will. And okay, so with those preliminaries, let me talk about what was kind of, I'll give a high-level description of the idea of Ding, Li, and Perez for connecting cover times to Gaussian free fields. All right, so here I've repeated the Ray-Knight theorem just for your reference. And okay, so the high-level idea is that the cover time is exactly corresponding to the first time that all local times are positive, right? So, so the way I've written here is that tau plus of t is below the cover time if and only if one of the local times up till time tau plus of t is 0. And again, as I was saying earlier, let's just think of tau plus of t as essentially being equal to 2 times e times t. Okay, so if one of these if one of these local times is 0, then in this left-hand side expression, I'm going to say, so let's say the local time at a certain vertex x is 0, then this expression at x should be, well, this part is 0, and then this part I'm going to say is kind of a small contribution, which we'll sort of be more precise about later. But we think of this entire left-hand side as being small if the local time is 0, which corresponds to this right-hand side being small, right? And right-hand side being small is saying that eta prime x is close to negative root 2t. And okay, so right, so here I've said that, right, so if one of these left-hand sides is small at some vertex x, then there has to be some vertex x here where eta prime sub x is like close to negative root 2t, so that's what I mean by this minimum here. And okay, so basically the key now is that for what values of t will this last event here transition from, I guess, being very likely to suddenly being very unlikely? Well, that's when root 2t equals m, right? Because right, if I compare the minimum against something much larger than negative m, then it's always going to be less than something larger than negative m. But then, right, okay, so basically this is because the minimum is concentrated near negative m. And then so if that's the threshold where this flips, then it suggests that the cover time will be, so then t would be m squared over 2. So then this suggests that the cover time would be about 2e times m squared over 2. So that's e times m squared. Yeah, so what Ding, Li, and Peres proved is that the expected cover time is equal to e m squared up to a multiplicative constant.
So actually, this
Yes. So it's an arbitrary graph. So it is somewhat relevant. Like, well, so yeah. So this is for an arbitrary graph, but it will be somewhat relevant whether root r is much less than m, which we'll see a bit more about later. So okay. So the sharper result that we're going to prove is that following conjecture of Ding is that is this here. And let me just describe what the expression means. It's basically saying that the cover time is concentrated around e m squared with fluctuations of order at most e times root r times m. So yeah, so as I was saying before, if root r is much less than m, then this means that the cover time is actually concentrated around em squared. And let me sort of describe this in another way, which is that recall that r is actually basically like, well, r times e is basically like the hitting time, the maximum hitting time. And then as we saw before, the cover time is basically like em squared. So the condition root r is much less than m is actually more or less the same as the condition that the hitting times are all much less than the cover time. And so what we have here is basically saying that so another I guess an implication of this is that the cover time is concentrated around em squared as long as the hitting time is much less than the cover time. And let me mention that Ding actually already proved this for trees and bounded degree graphs. And actually, one more thing is that there's actually kind of a converse to this due to Aldis, which is saying that if the hitting time is of the same order as the cover time, then actually you do not have concentration of the cover time about its mean, which kind of makes sense because the hitting time should it kind of makes sense of thinking of the hitting time as like the fluctuation of the cover time. And maybe at the end I'll return to that briefly. So yeah, okay. So that's the main result here. And maybe I should also mention that so now this means that if you can calculate m, then you can calculate the cover time in a lot of situations. And so in particular, there's a polynomial time approximation scheme for calculating the maximum of a Gaussian process like this due to Ragu-Meka. So this can give you potentially a way of calculating the cover time. And yeah, and I think that that thing also made an appearance in the heavy hitters talk. Okay, so this is the sharper result that we're going to try to prove. And now let me return to that argument I outlined earlier here, right? So I'm going to sort of fill in some details and make it a bit more rigorous. So let's first start with the upper bound, showing that upper bounding the cover time, showing it's not too large. So the way I'm going to explain this is a little bit, I guess, reversed somehow, but hopefully you can follow along. So let's think about it this way. Like, suppose for some value of t, it's actually quite likely that one of the local times is still 0, right? Then I'm going to show that t is necessarily small, okay? So let me just say it again. So suppose, I have some time, so I have some value t, and for some reason I haven't visited all the vertices yet with pretty good probability. Then that means I haven't gotten to the cover time yet, and I'm gonna try to show that this means that t has to be pretty small. So this is another way of, if you think about it, it's another way of saying that the cover time can't be too large. Okay, so how does this argument work? Well, if the local time is likely to be 0 for some x, then this left-hand side of the Ray-Knight theorem is likely to be small because simply because we have the local time being 0 for some x, and then for that x we have an independent Gaussian here, which has variance at most r. So it's not likely to exceed. So the sum of these two is not likely to exceed r. I guess by not likely, I mean there's a decent probability, like, at least 0.1 probability that it doesn't exceed r. But then what is this entire? So basically, yeah. So I'm basically saying there's a decent probability that one of these a sub x's is actually quite small being less than r, and that means correspondingly there must be a decent probability that one of these bx's is quite small, right? And then, but then the problem here is that how can bx be very small, that means eta prime x has to be close to negative root 2t. And as we said before, that that can only work when if root 2t is a lot bigger than m, then there's no way these things can get low enough to make that happen. So, okay, so this is filling in some details. If this was a little confusing, it's not super important that you followed this completely. Okay, so then the lower bound is a little bit more important for our purposes. So the lower bound is, suppose that root 2t is actually pretty small, okay? By pretty small, I mean like m minus some large constant times root r. Then basically what I want to say is that, well, okay, so let me put it this way. Suppose that eta prime x plus root 2t is actually equal to 0, right? Then that would immediately imply that the corresponding a sub x is equal to 0. So in particular, like all these terms are non-negative, so in particular, the local time is forced to be 0, right? And yeah, and I guess the point is if root 2t is much less than m, then this eta prime x plus root 2t actually has a good chance of being equal to 0. But of course, exactly equal to 0 is a very these are continuous. These are like real valued things, right? So exactly equal to 0 is not really going to happen with any positive probability. So but we kind of want to think, we want to say that somehow that phenomenon of this guy being 0, forcing this guy to be 0, should still be should be capturing like what is really happening. So so the argument that you kind of want to try to make is that if this thing inside is actually negative, then it also forces this local time to be 0. Okay, so I mean, it's not clear how to actually make that argument rigorously, but that's kind of a thing that you might want to try to do. The problem, of course, being that if this thing goes negative, you square it, it becomes positive again. So it doesn't really tell you anything immediately. So yeah, so this is kind of the obstacle I was talking about. And so in the original paper of Ding, Li, and Perez, they actually worked around this using majorizing measures. And okay, so missing step is to make this rigorous, and Ding also actually was able to prove this. By prove this, I mean like basically make a coupling between these two that for which this phenomenon is true. I mean, you could there's sort of an arbitrariness in the coupling because of this square, but anyway, so Ding was able to prove this for trees, but not for general graphs. So so at the end here, I'm going to talk about how to actually prove this for general graphs. Okay, so this is just a recap of what I was saying in this part. I guess this might be a good time to pause quickly if there are any questions, but yeah, this is stuff I already said. Okay, so now let's move on. Oh, was there a question? No. Okay. So so now let's move on to the third part, which is basically to prove that the sort of sketchy implication from 2 slides ago. So okay, so this is basically the thing that also appeared in a paper of Lupu, but not really applied to cover times. And Okay, so you don't have to parse this exactly what this thing says, but it's basically saying if I want to show that there's a coupling where if this eta prime x plus root 2t goes negative, then it forces the local time to be 0 on the left side. So the main idea is to actually, okay, so let's say we have these 3 vertices x, y, and z in our graph. We're going to actually do a refinement of our graph, which is to break each edge into n pieces. And yeah, so let's label them u1 through un minus 1, v1 through vn minus 1. And basically, I'm going to simulate the random walk going from, let's say I'm at x in the original graph, right? I just go to y or z with equal probability. I'm going to simulate that on this new graph where I introduced more edges by just doing a random walk on the new graph. And the point is, if I start at x, right, I'll go to u1 or v1 with equal probability. Let's say I go to u1. Then I'm going to walk along this edge for a while until I either go back to x or I hit y, right? The chance of hitting y is basically 1 over n once I'm at u1. Otherwise, I'm just going to go back to x. So basically what happens here is I'm going to return to x a geometric number of times until I finally reach y or z. So here, basically the walk on the refined graph visits x a number of times which is geometric with mean n before finally getting to y or z with equal probability. And so this means if we ignore all the visits to these intermediate vertices, we've basically simulated the random walk on the original graph. And also recall that each waiting period is exponential. So a sum of a geometric number of independent exponentials is still an exponential. So even on this refined graph, the time spent at x is still an exponential random variable before hitting y or z. But it's normalized differently. Like I guess the expectation is n instead of 1. So you kind of have to renormalize things. But the point is that the random walk on this refined graph is kind of the same, and also the local times are kind of the same up to renormalization. And then Gaussian free fields are also related in a natural way because, well, it's just because if I replace a single resistor by n resistors in series, that just multiplies all the resistances by n. So again, the Gaussian free fields are, at least for the values, eta x, eta y, eta z, those are going to be more or less the same, except there's rescaling involved. So then we're going to think about what happens as this n goes to infinity, and this limiting object is known as a metric graph, which is just like a graph, the vertices, and then you also include the entire edge as well, like every single point on the edge. And okay, so in the limit, the random walk basically becomes a Brownian motion on the edges. And the Gaussian free field, well, as we said, at the vertices like x, y, and z, it has the same law up to rescaling as the original graph. And then I guess we also want to describe its values along the edge. And it turns out that's just going to be a Brownian bridge. And that's just basically because of it's more or less the same calculations you do to show that the Gaussian free field for a path is just a Brownian motion. So yeah, okay. So yeah, so the Gaussian free field, let me just emphasize on the metric graph is sort of this continuous function that takes values at x, y, and z, but also all the way along this whole edge. Okay, so why did we bother with all of this stuff? Well, it turns out that applying the Raynight theorem to this metric graph will kind of enforce the correct coupling on the original graph in the following sense. So by the Raynight theorem on the metric graph, these two processes, I guess maybe I shouldn't have used v here. So this is really supposed to be x not only in v but also on each point on each edge of the graph. By the Raynight theorem, these have the same law, so you can couple them together to be equal. And then the point is, now let's consider the set on which the local times are positive. And okay, so for the metric graph, the local times are actually because we took a limit, they're actually like local time densities. So it's a little bit different from the original setting, but okay. So I want to claim that this set on which the local times are positive is almost surely connected, which makes sense because if my local time is positive somewhere, that means I've actually visited there. So there should be a path I took to actually get there, and so my local time should be positive all the way along that path. This is not. It does require some justification because of this limiting thing I did. So, you can have positive things, but in the limit they go to 0. So this requires some justification, but I think if you think about it, it should be pretty plausible, and indeed you can show it. And then okay, and then again, as before, if this eta prime x plus root 2t equals 0, it forces the local time to be 0. And then now the final thing is that this means because of this continuous limit that we pass to, we see that this eta prime x plus root 2t can't change signs on the set U, right? Because if it changed signs, then by the intermediate value theorem, it would have to be 0 somewhere. But that's impossible because U is the set on which local times are positive. So this thing here can't change signs on U, and it's positive at v naught, and U, of course, contains v naught. So it follows that this quantity here is positive on all of U, which is exactly the thing we wanted to guarantee, right? Well, I guess it's like sort of the converse. Like if the local time is positive, then this eta prime x plus root 2t should be positive, or equivalently, if this root eta prime x plus root 2t is negative, then the local time should be 0. And so that completes the obstacle at the end of part 2, and yeah, and then so that basically completes the proof. And let me so I'll quickly mention two sort of outstanding questions. Well, kind of. So one of them is that the only known proofs for the Raynight theorem are calculations in some way. I think there are some proofs that are maybe. I mean, there's some very tricky ways to do the calculations, but at the end of the day, I don't think anyone can really say that they like completely understand, exactly why this would be true and why it shouldn't be surprising or anything like that. So that's one thing that's still quite mysterious. And then another thing I want to quickly mention is that back here, okay, so back here, we found that the fluctuations are like e root r times m, but one might think one might think that the fluctuations can actually be e times r. So I'm not sure if this should hold in complete generality, but something interesting to think about would be to see if you can show that the cover time has fluctuations of order equal to the hitting time. And yeah, in particular, I think this is like a sort of a somewhat long-standing open question for the discrete torus. I don't know if I can say long-standing, but open for a while. Are you think they're close to solving it now? Okay, so maybe they're close to solving it now. Yeah. So okay, but anyway, so that's it. Thanks for your attention, and I'll take any questions. Yeah. Right. So I said that. It should be basically the same for discrete, and it's just because the transformation is pretty minor, right? It's just instead of deterministically having t steps, I have the sum of t IID exponentials, which is pretty concentrated around t. Yeah. So it should be pretty much the same. Yeah.
You mentioned that this Gaussian free field for a path can be viewed as a Brownian motion.
Yeah.
So for a general graph, is that some?
Not really, I guess. Yeah, I don't think I have a particularly good way of describing it. Yeah, so